Welcome back to our discussion regarding weathering processes on the Earth's surface. We've completed part one, where we looked at the difference between mechanical weathering and mechanical weathering and chemical weathering processes, where we outlined some common processes with mechanical weathering, such as frost wedging, exfoliation, and human intervention. Then we looked at chemical weathering, where we identified a very common chemical reaction that takes place on continental granitic type rocks, where we change the orthoclase mineral into a kaolitic clay mineral. And we learned in part one that most types of rocks found on the Earth's surface is eventually reduced down to the last weathering type product, which we can just known as clay. So we're going to continue on with the discussion in part two, and now we're going to take a look at soil. And the next 4 or 5 slides cover what soil represents, how soil is distributed throughout the Earth's surface, and we're also going to look at how soil is categorized or grouped or classified. And this is about 4 or 5 slides or so. And really what we're doing is we're giving you a bachelor's degree in soil science within about 5 slides. So looking at soil, by definition, soil is a product of weathering. And typically soils will contain a solid, liquid, and a gas, which again differentiates that from lots of material or many material found on other planets. So solids, liquids, and a gas. So what's in your soil? And so that comes from that little saying, what's in your wallet? But in this case, we're looking at what's in your soil. To start with, a soil must contain what we refer to as a loam, which is a dominant fraction of grain sizes between sand, silt, and clay. And whenever you pick up a handful of soil, there will be a certain percentage of varying between the sand, silt, and clay. And to measure that, we use what I like to call a ternary diagram, or a soil ternary diagram, which you can see located on the right side of your slide here. And in the soil ternary diagram, we can classify the loam by looking at the various percentages that are represented in this diagram. So let me kind of outline this diagram and show you how this diagram works. So again, it's a triangle, and at each corner of the triangle exists 100% of the particular type of soil fraction. So for example, where you see my arrow, you see that at this part of the triangle is 100% clay. And then you come down to the this part of the triangle where my arrow is. This is 100% sand. And then over to the right at the triangle is 100% silt. And anywhere in between the points of the triangle is a percentage of sand, clay, and silt. So, for example, we can go back to the sand percentage down here where it says 100% sand. And as we move away from the 100% sand, we become 90% sand, 80, 70, 60, 50, 40, and so forth. And the same thing takes place with the silt and clay. So in order to measure then a certain clay, sand, silt percentage, we're going to look at what happens inside the triangle. So for example, we put a little dot right here, and here comes the little dot. We are going to find what the sand, clay, and silt percentage is for this particular point in the triangle for a sandy clay loam. And the way we're going to do that is we're going to use these little yellow lines inside the triangle. So for example, for sand percentages, all the yellow lines are going to parallel and follow this arrow down here. So this is a sand percentage, that's a sand percentage, sand percentage. For clay percentages, we're going to look at the arrows that cross the triangle in this fashion. If you look at my arrow on the screen. So 50% clay here, 60%, so forth. And for silt fraction, we're going to follow this arrow in terms of the lines paralleling this arrow. for silt. So 50% silt, 40%, 30%, and so forth. So to then calculate or look at the percentage for the red dot that we put in the triangle, we're going to do it this way. And we can choose sand, clay, or silt. Any one can be first, but in our case, we're going to choose sand. And so we can see that 50% line of sand follows right here. And we can see that the 50% line goes right through the red dot. So we know that there's 50% sand. And then clay, for example, is the 30% line here. So we know that it has 30% clay, and we know it has 50% sand. And the beauty behind this diagram is that all the percentages must always add to 100%. So if you know two of them, you can certainly get the third one. So if we have 50% sand, 30% clay, that's 80%. We would expect then to have 20% clay. And sure enough, 20% silt. And sure enough, you can come up to this line and you see 20% silt right here. So it's going to be your job to practice using this loam ternary diagram. And what you should be able to do by exam time is to plot any dot within this circle, and you should be able to calculate the concentration of the sand size, silt size, and clay size. And so, for example, we'll do another one. I'm just going to put my arrow on an area. Let's put my arrow right here. So let's find out what the percentage is for a silty clay loam where my arrow is. And what we can see then is that in this case, the sand is 10% and the silt is 60%, which must mean that the clay must be 30%. And sure enough, it's right there. Okay, so for this red dot, we should have gotten 50% sand, 20% silt, and 30% clay. And this particular material then would be classified as a sandy clay loam. So that means that you should be able to go out into your backyard or any place and actually scoop up soil and have some mixture between sand, clay, and silt. And when I was younger, wearing younger man clothes, I worked for a soils company, and one of my jobs was to calculate the sand, clay, and silt percentages of various samples that came in from all over the Santa Barbara area where I lived. And the way we did that is that we would take a shovelful, if you will, or a scoop of material. We would weigh that material and get some kind of weight on it. And then we would take these canister sieves, and then we would separate the sediment or separate the unconsolidated material into a sand sieve, silt sieve, and a clay sieve. And then we would weigh each one of those individually, and that would actually turn out and give us a sand, clay, silt proportion or concentration. And in civil engineering, especially in soil science, understanding this percentages between these sand, clay, and silt fractions was helpful to determining on how to build a structure, for example, on the surface. Very helpful for folks that have gardens, because you don't want a garden that's too clay rich. You don't want a garden that's too sand rich. And so I'm sure in terms of a garden, you're looking for something that's right, pretty balanced between the sand, clay, and silt, for drainage purposes. Now, one of the things I noticed on this diagram, which stands out, is if you look at this diagram, what fraction between sand, clay, and silt stands out the most. And if you're looking at this diagram, hopefully you're saying it's the clay area. And so there's dominantly more clay in this diagram than the sand and silt. And the question would be, why is that? Well, if you refer back to the previous slide and looking at part 1 in weathering, we find that clay represents what? Clay represents the end member, or the most reduced material to be chemically altered, and decomposed. So you can't decompose, or you can't break clay down into any smaller fraction. So in this case, because of that, clay dominates, the ternary diagram. So have fun with that, but you want to be able, again, to calculate percentages between sand, clay, and silt using this diagram. So what's in your soil? Loam. And how about humus? And humus represents partially decayed organic material. So to be a soil, you got to have organic material within that soil. And that's reasonable because that organic material would dominantly come from decayed plant material that lies on the surface of the earth. Or how about decaying animals? Animals die, they lay there, and they decay as well. So humus, to be a soil, it's got to have carbon dioxide, it's got to have air, typically filling in the soil voids. And so certain soils have certain amounts of porosity or space in between the grains. And of course, they're filled by carbon dioxide and air. And how about water? And water, of course, wets the entire soil. And water is very instrumental in percolating through soils and carrying levels of dissolved substances, and mostly dissolved ions, dissolved substances. And water kind of is able to transmit and move through the soils. Now, one of the relationships we can look at here in terms of what's in your soil is the relationship between the amount of water that's in your soil and carbon dioxide gas that's in your soil. Because if you think about it from part one of the weathering discussion, what did we talk about regarding the reaction between water and carbon dioxide? And right now, hopefully you're saying, wow, that's carbonic acid. Because remember, when you add carbon dioxide to water, it produces that weak solution of acid, carbonic acid. And we learned in part one that carbonic acid is instrumental in changing and decomposing and chemically altering materials. And it's not any different that when carbonic acid is in the soil as well. So with what's in your soil and the different characters of your soil, soils can form all over the Earth's surface. And in terms of describing how that soil forms or what characterizes that soil is we use a characteristic called soil profiles. And soil profiles typically represent layers. And so if you were to take a backhoe, for example, in your backyard or anywhere on the Earth's surface, and you were to dig down 5 or 6 feet, and you look at the cross-sectional view of your where you dug, you would probably come across little tiny or various layers of the soil. And so we're going to replace that name layers, and we're going to replace that term call the layer horizons. So each soil profile has a set of horizons. And a horizon represents a layer of soil in which, in that little layer or that horizon, there is a distinctive physical and chemical property associated with that layer. And we're going to find out later that there are several factors on Earth that play a very important role in determining these distinctive physical and chemical properties of each one of the horizons. So we're going to take a look at what we call a typical classic soil profile. And we're going to be a soil scientist, and we're going to label each one of the horizons and then look at some of their distinctive physical and chemical properties. So layer one, or the horizon number one, typically occurs at the top of a soil profile, typically a dark color horizon, and it's termed as the O layer, or what we would call organic matter, in which it's dominantly humus material. So this is where we have a lot of decayed organic material. And again, that would be reasonable to find that at the top of a soil profile because of the fact trees die, animals die, and that's where organisms and organic material begins to decompose. So now envision and picture then this soil horizon, and picture the O layer now being infiltrated with water. And so as it rains and water gets on the surface, rains begin to percolate, transmit and move through the organic layer. And so, of course, with that water, it's going to carry with it ions and mineral material. And now it's deposited in the layer or horizon below the O layer, known as the A layer, which is a mixed mineral and organic matter. So this is where the water basically takes out, pardon me, takes out dissolved material from the O layer and again deposits it in the A layer, mixed mineral and organic matter. So as the water continues to percolate and trickle down and move through the soil horizons, it now begins to leach dissolvable or soluble material from the A layer. And when we say soluble, we're talking about material that's easily dissolved into the water, and it basically leaches the A layer, and now it moves into depositing a very light colored layer, and this is known as the E layer. And so continue percolation of water, continue chemical decomposition. We now finally move into the B layer or B horizon, and the B horizon represents the accumulation of clay. And so now we go back to this question, and that is, why is typically the B layer or the clay horizon at the very bottom of a typical soil profile? And you probably have answered it already, and that's because, again, clay represents the most chemical reduced material. And so as the water percolates through O horizon, A, E horizons, it finally has decomposed those horizons and now accumulated the clay in the B horizon. And the last horizon typically associated with a typical soil profile would be the C horizon, which is known as what we call weathered parent rock. Now, given the fact that we have the C horizon as the weathered parent rock, out of these horizons O, A, E, B, and C, which horizon do you think was first before any other horizons began to form through weathering processes? And the answer to that would be the C, the parent material. In other words, what this soil horizon represents is that the parent material was there first, and as the parent material sat there through geologic time, allowing weathering processes to take place, the water, and maybe in this case, has slowly decomposed and changed the weathered parent material into the O, A, E, and B layers. So again, this is what we would known as a typical soil horizon or soil profile. And if you were to go into your backyard and dig a ditch and look at the horizons, you may not necessarily find all of these horizons, O, A, E, B, and C together, because it really depends on a whole host of different conditions and factors, which really means that there are numerous, if not thousands, of soil profiles produced all over the Earth's surface because of various conditions and various factors. But again, what we're showing you here is what we call a typical or classic soil profile. Now, when you take the exam, you're going to be asked on the exam, what horizons in order typically represent a typical soil profile. And it's easy to memorize O, A, E, B, and C, but that's not the way the answer is going to be approached on the exam. Instead, you'll need to know the meaning for what we call the O layer, the A layer, and the meaning to the E and the B layer, and C and so forth. So as you prepare for the exam, learn your soil horizons as a descriptive of the physical and chemical property as opposed to just memorizing the letter. So, factors that influence soil formation. So again, the previous slide showed you a classic, typical soil profile, and we understand that you're not always going to find that particular soil profile. Why? Because there are factors that influence soil formation. So there's about 5 or 6 of them, and let's start with the first one, and let's look at what we call parent material. Parent material represents the soil. Well, there's 2 types of parent material. The first one is residual regolith, and residual regolith is a type of soil profile that forms in place. In other words, it doesn't move. And that was the previous example that we showed in the previous slide, that the parent rock was there first, and then the parent rock is slowly decomposed into the various soil horizons. Sometimes the term in situ is used to describe a residual regolith or a soil that forms in place. So this diagram below kind of illustrates the previous soil profile that we showed in the previous slide. Here is your parent material. There's the sea horizon. And then if you look at my arrow at the bottom of the diagram, this would represent time, and time would move on. And as time moves on, the parent material begins to decompose, and maybe that now forms the A horizon, and then further decomposition and weathering of the parent rock now forms the B and the A horizon, and so forth. So this is a good example of a residual regolith, or a soil that is formed in place without being moved. And so this diagram to your right shows you a description of a typical residual regolith. And then here on this side of the diagram, the right side of the diagram, you can see where you see the various horizons. So if the parent material then is residual, the opposite of a residual soil could be a transported regolith. This is regolith that is moved typically by some type of transportation mechanism, in this case, rivers, wind, and ice. And so this would be an example of a transported type regolith. Here we show river deposits. A geologist can easily identify a river deposit just by looking at how the horizons, if you will, and the soil material is being distributed and laid down. And so this would, again, this picture would represent a river deposit. This picture here, I've always liked to ask the class if anybody's ever been here. And I get a few people that raise their hand. And then I tell them, well, no, you probably haven't been there, or maybe you have, you're just not telling anybody. But this is regolith transported on Mars. And so Mars really is only regolith. Mars really doesn't have soil horizons, because what does Mars lack that Earth has? And Mars lacks a hydrologic cycle, or water. And so really the Martian surface is really relegated only to regolith. And that's what you're seeing down at this picture. Okay, so parent material is one factor. Let's look at a couple more factors. How about climate? And so soil profiles will differ around the world, which is directly influenced by the climate. For example, you can have soils that form in tropical regions where there's lots and lots of water, or you can have different soils form in arid regions where you have lack of water, because arid is another term for a desert type environment. Living organisms is a big influence on soils for many reasons, because those soils can be transported by the organism, plus introduction to organic matter, and the animals mix the soil and recycle the water, and that would produce different kinds of soil profiles. How about topography? Topography really is a term that is used to describe the lay of the land, where you can have mountains and valleys. And so the contour, or the mountains and valleys topography of the land, can certainly produce different kinds of soil profiles. For example, you are more likely to see a thicker soil profile down in a valley versus a thinner soil profile up in the mountains. And that's directly due to weathering and gravity, because under gravity, materials are brought down into the valley, and the mountaintops are a little bit thinner. So that can change it. And finally, probably the biggest influence and biggest factor that can determine a soil profile is the last bullet point on the slide, and that's time. And the longer time, more geologic time that's evident and present, the more mature the soil becomes. And sometimes it takes thousands and thousands of years to create a very defined set of horizons to kind of show a soil profile. So you can see then that the factors that influence the soil formations, we have about 1, 2, 3, about 5 of them. And because of that, you're going to now have different soils all over the world, because you have all these factors contributing and intermixing with one another, producing different kinds of soils. So if that's the case, then you can imagine that classifications of soil becomes somewhat complex, and you're dealing with thousands and thousands of different types of soil profiles. So classification of soils is a science that deals with what we call soil taxonomy. And the classification of the soil is typically based on physical and chemical properties of the soil profile. And as we learned in the previous slide, those physical and chemical properties are influenced by all of the factors that we just discussed: climate, living organisms, topography, time. Is it residual? Is it transported? And so forth. So again, based on that, you can imagine, if you're a soil scientist, how many different kinds of soils can be classified. And so like anything else in the sciences, soils are no different. Scientists love to classify and categorize and put things in certain kinds of order. And so we're going to do the same thing now with classification of soils. So there are 6 categories of soil classification. And you can break that classification of soils down into order, suborder, great groups, subgroups, families, and series. And typically the order will represent the most broadest set of soils based on describing the physical and chemical properties. And there are about 12 broad orders that can be classified across the world. And you can take the order, break it down into suborder, then great groups, break it down into subgroups, family, and finally you get the series. And by the time you break down all the 12 orders of soil break down 12 orders of soil, and you get down to the series classification, you end up with about 19,000 specific types of descriptions of different kinds of soils. And so because this is not a soils class, certainly we are not going to look at the specific details of physical and chemical properties of 19,000 different kinds of soils, but instead we will look at the 12 orders of soil, and we'll look at the most broadest group of soils across the world. And these names of the soils are derived from Greek names, Latin solum for soil. So in most cases, the broadest orders of soil will end up with a suffix as SOLS, sols. So you can read down the list. You have alpha sols, andisols, aerosols, entosols, gelisols, histosols, septosols, molysols, oxysols, spotosols, utosols, and vertisols. And when I was going through my experiences in my community college, I was a geography major. I actually minored in geography along with my geology. And one of the activities we had to do for our geography class is learn all the soils. And when I say learn the soils, learn the broadest of the 12 orders. And so what I usually do in the face-to-face class is I have students learn the 12 soils. And you can take a flashcard, for example, and you can write on one side of the flashcard alpha sol, and then on the other side of the flashcard, you would write high nutrient soil. Or you could, same thing with an andesol. You would write andesol, and that'd be a volcanic soil, and so forth. And so for this class, it's no different. If I had to learn them, you can learn them. However, you'll have a little better access to them during the exam time. So be prepared during the exam to match the different kinds of soils and their descriptions. So for example, if somebody says, what's an entisol? You should be able to say, oh, that's a new type of soil, and so forth. This next slide shows a map view, or a world map view, that shows the distribution of Earth's soils. And so first of all, you look at the map and you see lots of varying colors on the map. Those are indicative of the various types of soils across the world. Each one of the colors represents one of the broad order of soils, so it's one of the 12 orders. And if you kind of take a look back at the map and just kind of look at the varying of the colors, you should see a distinct pattern of colors. And like everything we do in the sciences, we always look for patterns. And so, for example, if we draw the equator across the world map, you can see that the equatorial zone on land masses are marked by the red color, which is equivalent to the oxysol, which is typical to tropical forest soils, which are soils that are very high in aluminum. And these are soils that are created from the high abundance and amount of water. And then, of course, you can look at other patterns. And if you look at the pattern in which you go 30 degrees latitude south of the equator and 30 degrees north of the equator, you see that these soils are kinds of in the orange-yellow zone. And these are typical soils known as aerosols or desert soils. And there are process reasons why there are deserts 30 degrees north and south of the equator. Later, when we get into winds and global winds, we'll talk a little bit about why that pattern exists. So I was looking then when I was preparing slides a long time ago for this presentation. I thought, well, the San Joaquin Valley would be a very interesting place to look at the classification of the soils. And so I asked the question, what soil type or order characterizes the San Joaquin Valley? And so what I was looking for was just the broad order type that would encompass the entire valley. And the first question we have to ask is, what is the San Joaquin Valley noted for? And most students will raise their hand and indicate that we're noted for agriculture. And we're actually noted for the fact that the San Joaquin Valley can supply a large percentage of the world's vegetables and stuff that comes from agriculture. And so I said, okay, well, what would be the order then that characterizes that? And do you realize it took me over an hour to find out or look at or confirm what order characterizes the San Joaquin Valley? I already knew what it was, I had a good idea, but I wanted to confirm it. And really what I had run into when I was researching this is that the San Joaquin Valley is divided up into series. It's divided up into specific soil types all up and down the valley. And there's a good reason for that, because the San Joaquin Valley's been extensively studied from an agriculture point of view in terms of the physical and chemical properties of different areas of their soils. And that's important because one must be very, very well educated in agriculture to know what to grow. And so the San Joaquin Valley has been extensively studied. But anyway, at some point, I haphazardly came across a confirmation in terms of what the order is that characterizes San Joaquin Valley. And of course, those would be alpha sols. And if you look at an alpha sol is classified on the basis of order as a high nutrient soil.